Welcome, ladies and gentlemen. Let's go ahead and take a look at our Bellwork for today. As we consider our right triangle, what equation relates x, y, and r? Courtney?
X squared plus y squared equals y squared.
Awesome, thank you. Our Pythagorean theorem relates the leg lengths to the hypotenuse length of any right triangle. Thank you. Write x and y in terms of theta. So what will x look like in terms of theta based on our picture? Vivian? R times cosine theta. Thank you. And what does y look like in terms of theta? Grace?
Sine of theta.
Did you say times r? Absolutely. Good job. And so where do these come from? What my x equals and my y equals? Well, same thing. They come from my picture. If I consider my right triangle trig ratios from my original picture, I know that my reference angle theta, right, is related to the opposite and the hypotenuse via the sine function. So we could start from the beginning and say sine of theta is equal to the ratio y over r, and then solving for the y, right, would be multiplying r to both sides. The same is true for my cosine ratio for x. I would have adjacent to my reference angle theta, adjacent over hypotenuse, and so cosine of theta would be given by the ratio x over r. And again, solving for x would be multiply r above both sides, and that's how I get x. Awesome. So we need to get that from our parametric equation activity. Raise your hand if you had number 1 and 2. This first slide all correct? You got 1 and 2 correct? Good. Thanks. Let's take a look now at a relation, right, given by the parametric equation x equals negative t squared plus 1 and y equals t plus 2. We could take those t values, my parameter, right? I could take those and then to generate my y coordinates, right, for these particular selected t values simply by plugging it into the y equation for t and working it out. Same is true for my x coordinates. So let's go ahead and list, right, my x coordinates in order. Keep in mind you're going to square first and then apply the negative. So what did you get from your x's? Let's just go top to bottom in the interest of time. Danny?
Negative 8, negative 3, 0, 1, 0, negative 8.
Thank you, Danny. Raise your hand if you have the same x column. Great, thanks. Hands down. My y column, top to bottom, please. Sophia?
Negative 1, 0, 1, 2, 3, 4.
Awesome, thank you. And raise your hand if you have the same green y column. We're good to go. Thank you. Let's make our points. And so when we have our x comma y is still plotted in my xy coordinate plane, the Cartesian coordinate plane, the same as before. At a t value of negative 3, it looks like that points to the point negative 8 comma negative 1. We can just get it right there. Negative 3 comma 0, 0 comma 1, 1 comma 2, 0 comma 3, negative 3 comma 4, and negative 8 comma 5. If we connect these in a nice smooth relation, keeping in mind the order in which they're plotted, as t increases, we could even add those little arrows, and I kind of did that on the activity keys. So as t increases, right, it kind of traces in this path. Now, that's not necessary for your graph. The relation it points to is just the collection of points, right, connected together like we're used to thinking. However, this is going to help us today when we're constructing our polar graphs as we consider the values of theta increasing from 0 to 2 pi or whatever window we're specifying. We can see how the curve is being created in the polar coordinate plane, and so we can use kind of the parametric equations as a jumping off point. In any case, raise your hand if you had this blue picture. So who had this blue picture correctly? Yes! Then we're halfway where we need to be. Are we able to rewrite our equation number 3 in terms of x and y only? And so I went ahead. Oh, you guys didn't know that there was a number 4, did you? Pesky bugger comes in on the first side. Well, we can do it right now then. In your activity, you had the option of solving, right, for x and for t in terms of x or t in terms of y. as you scan this parametric equation, is it going to be easier to solve for t in terms of x or to solve for t in terms of y? Sophia? In terms of y, how come?
Because that's a linear.
Yeah, absolutely. If we were to solve for t in terms of x, it looks like I have to undo squaring, and we know when you undo squaring, an even positive integer exponent, we have to consider both the positive and negative square root, and so that's going to be a more complicated scenario. So let's go ahead and do the second one. We could rearrange this and solve for t in terms of y. It looks like we subtract over the 2, so everybody go ahead and do that if you haven't already. So y minus 2. And if t equals y minus 2, I can now replace that, right, in my x equation, everywhere I see the t, to rewrite a relation in terms of x and y components. So I'll go to that first equation, x equals, and I'll rewrite it. X equals opposite of t squared plus 1, except everywhere I see t, I won't put t, I'll put y minus 2. You could stop here. This is a relation written in terms of x and y. In fact, some people would argue that stopping right here makes more sense than foiling that out, distributing the negative, and combining like terms. In this way, we can see that this is actually moved up 2 and to the right 1 and opens to the left. What? Up 2 to the right 1 and opens to the left. Do you guys see that? Okay, so in terms of transformations, if we apply those transformations, right, that we're used to thinking about y as a function of x, left, right, up, down, but now to this relation that we have x solved for in terms of y, we could see that that is in fact the graph. And so you could stop here. That's not to say that you couldn't keep going too. You could FOIL this out, distribute the negative, combine like terms, and that would also be acceptable. Just be careful with your negative signs. Awesome. And what questions do you guys have about today's Bellwork? All right. If you were able to complete the number 3 and then number 4 we kind of did together, then you're where you need to be in terms of parametric equations right now. Okay. This also will be a good springboard for our discussion today with polar graphing and polar equations. At this time, I'm going to go ahead and pause the recording because we're going to do our mammoth collection. So we'll go ahead and do activities first. Okay, ladies and gentlemen, and so you'll notice that your OTL number 3 ended with several trigonometric function graphs. And you might be thinking, where did this come from? Here we've been dealing with sequences, series, infinite series, parametric equations, and then bam, trig functions. Well, yes, today we're going to introduce polar coordinates and polar graphing, which are based on our trig function values. So we're going to use that then to help with our graph creation, and we'll be making a connection between our typical Cartesian graphs of the trigonometric functions and then now some polar curves, as well as introducing some polar function families next class with polar graphing activity. But today it's the introduction activity. So we've got 3B, 5B, and 11E. Only 3 stamps. Why? Well, it's fairly short. You're going to take a look at polar coordinates, see how they represent points in the polar coordinate plane. Then we're going to stop and come together and do some whole class graphing examples together so that you get an idea of what these functions look like and how we can create them by hand. And then next class we're going to do some more in-depth and generalizations with our polar function families. So we've got that to look forward to. So let's go ahead and scooch into our groups, and we'll come back together for some whole group examples, and I'll pause the recording again. Okay, ladies and gentlemen, nice job on your introduction to polar graphing activity. Let's go ahead and come together now and do some whole class examples. So at this stage, we're going to make a connection between what we already know about our Cartesian graphs of our trigonometric functions and our new polar graphs. So let's go ahead and find on your note sheet for day 6 our first graphing whole class example. S of x equals sine of x. Careful how you say that, Tyler. S of x equals sine of x. And let's go ahead and specify our window. We could do 0 to 2 pi. So I'll just go pi over 2, pi, 2 pi over 2, 2 pi. And then I could go 1, 2, -1, -2. So for our original S and X graph, we go 0, 0 in the Cartesian plane. Right, you guys did this last night in your OTL 3. Pi over 2, 1. Pi comma 0, 3 pi over 2, negative 1, 2 pi 0. Go ahead and take a minute and get a nice smooth curve on your note sheet. As you know from your introduction, the polar coordinate plane, right, specifies the magnitude away from the origin, that r value. That will in turn come from the function value in your original Cartesian plane. What? Well, consider, right, your function values as representing the value of r. So if I kind of drew my values of r here as the function value in the positive or negative direction, that's going to begin to help me to get points in the polar plane. All right, so let's go ahead and transfer our Cartesian points like 0, 0. Let's see what that would correspond to over here in the polar graph. So at a direction of 0 degrees now, right? 0 radians, the magnitude of r is 0. Well, that means the point 0, 0 in the polar graph exists. As I scoot now in the positive theta direction, right? We're rotating now in the positive theta direction. Consider the value of sine of pi over 4, halfway in between here. So let's look at this first r value, right, that I've drawn here. What is the sine of pi over 4? Well, it's root 2 over 2, right? Root 2 over 2, which just numerically is about 0.7. So if I were going in the pi over 4 direction, right, I'd go to about 0.7. Right about there. Yeah? Go ahead and plot that. Continuing on, what happens to my r values? Well, at pi over 2, what's the value of r? Well, the sine of pi over 2 is 1. So I need to go a magnitude of 1 in the pi over 2 direction. Where's that point? Right there. Did everybody see it?
Yeah.
Got it? Awesome. Continuing on, again, we're plotting this magnitude r away from the origin at a given rotation of theta radians. You guys see this? Okay, let's keep spinning then. And where are we spinning now? Well, an easy one again will be spinning until 3 pi over 4. Will that be an easy one to plot? So at a theta value of 3 pi over 4, that's right in here, right? What's the value of my sine function? Well, sine of 3 pi over 4 is root 2 over 2, which is about 0.7. So everybody, let's plot that. Right? Let's plot 0.7, comma 3 pi over 4. So that's about what here again? Yes? Continuing on, maybe we need some more. Do we need another one like 5 pi over 6? 5 pi over 6? So at 5 pi over 6, the value of sine of 5 pi over 6 is 1/2. So in the 5 pi over 6 direction, I need to go half. That's halfway to the stick mark. Halfway to that radius of 1. You guys see that?
Mm-hmm.
That'll be like right here. We need to go and add another one. Like, go back to pi over 6.
Mm-hmm.
So at pi over 6, what's the value of sine? We're back here. The sine of pi over 6 is 1/2. That corresponds to the point 1/2 comma pi over 6. So right here, pi over 6, I need to go 1/2. That would be halfway to the radius of 1 mark. Everybody see it? What's going on here? Well, if I continued plotting points, r comma theta, right in between, I'd see that this first portion of the graph, from 0 to pi in rotation, we've just traced out a circle. A circle whose orientation, when based on sine of theta, appears to have this sort of vertical left-right symmetry. You guys see that? Let's go ahead and do the second portion of our graph. The window pi to 2 pi, their theta values, and see how that shows up on our graph. I'm going to go ahead and switch colors here. Right? I'm going to switch colors here just so we can see where these secondary points are coming from. So everybody, we're going to continue on. Now I'm going to go ahead and use the black colored marker to generate these points so we can see where they're coming from.
That's less
Bless
cool.
you. If we said that my s of x, my function values, are going to correspond to our radius magnitude values, right? Then whenever we have a negative function value, I'm going to be plotting in the negative direction because negative r values cause the negative direction. So let's go ahead and consider another key point. How about at pi, right? At pi degrees, or sorry, radians of rotation, the value of sine is 0, which means I need to plot the point 0, comma pi again. So I'm going to plot in the pi direction. I'm going to plot 0. Yes. Next, right after pi radians, we could do 7 pi over 6. We know 7 pi over 6 is about right here. What's the value of sine of 7 pi over 6?
Negative 1/2.
Negative 1/2. So I need to plot a negative 1/2 magnitude, right, in the 7 pi over 6 direction. First, let's find the 7 pi over 6 direction. Right here. This is the 7 pi over 6 direction. Yes? Could I plot negative 1/2 in the 7 pi over 6 direction? Yeah. Negative magnitude means opposite direction. So I'm going to plot right there. Keep spinning. Just keep spinning. Just keep spinning. Let's do 5 pi over 4. That's an easy direction. So 5 pi over 4 would be in this direction. 5 pi over 4. What's the sign of 5 pi over 4? Negative root 2 over 2. Can we plot negative 0.7 in the 5 pi over 4 direction? You bet your boots we can. We're going to go in the opposite direction about 0.7. You guys see it? Just keep spinning. Just keep spinning. Let's go to 3 pi over 2. What's the sign of 3 pi over 2? Let's plot negative 1 in the 3 pi over 2 direction.
Wow.
Ah, very nice. It's good. 11 pi over 6. 11 pi over 6. The sign of 11 pi over 6 is negative 1/2. I'm going to plot negative 1/2 in the 11 pi over 6 direction. That's right here. Oh, feel like we already had that. Because we do. So this second range of R values that I've shown with the black arrows designating the R values, just trace out the circle again. So it appears as though, right, if we continue going on, now we've completed one full cycle in my regular Cartesian. If we continue the sine graph forever and ever and ever, we continue tracing out this circle, right? This circle in the polar coordinate plane. Interesting. So this is just an introduction. We're seeing kind of how we can use that to create the graph. And we're not making any generalizations or conclusions just yet. That's going to be more for next class. Let's take a look at another. Let's look at our basic cosine function in the Cartesian coordinate plane, c of x. Again, we can specify our window. Let's go 0 to 2 pi. In the Cartesian coordinate plane, cosine starts at key point 0, comma 1 at max and rotates through my cycle at quarter period intervals. Max, center line, min, center line, max, center line, min, center line, forever. Let's now use our function values of c of x, right, and use those to generate our r values in the polar coordinate plane. Again, I'll go ahead and use some colored markers here to designate those points. Let's go ahead and start at a direction of 0 for theta. Cosine has a magnitude of positive 1. Can I plot positive 1 in the 0 direction? Well, 0 radians is in this direction. Can I plot positive 1 in the 0 radian direction? Yeah, where would that be? Right here. Maybe this one, too. All right. You guys want to do pi over 4? What's the cosine of pi over 4? Root 2 over 2, right? Which is about 0.7. Can I plot a radius of 0.7 for magnitude in the direction of pi over 4? Yes. We're about there. Yes? Let's keep spinning. When I get to a direction of, well, we're going to do one more. We can do one more. Let's do pi over 3. So pi over 3 will be that direction. In the pi over 3 direction, I'm going to take my cosine function value and make the corresponding radius value. So what's the cosine of pi over 3? The cosine of pi over 3 is 1/2, right? So in the in the pi over 3 direction, I'm going to plot 1/2. So that would be halfway to that first radius mark. Is that about there? Yeah? Halfway? Cosine of pi over 2. Plot a radius of 0 in pi over 2 direction. Now we have, right, a portion of the cosine graph with negative function values. Negative function values on my cosine Cartesian graph is going to correspond to negative r values on my polar graph, and we know how to plot those. Negative r values mean opposite direction plots. So let's go ahead and consider a convenient one in this range. How about 3 pi over 4? 3 pi over 4? So in the 3 pi over 4 direction, let's see, cosine of 3 pi over 4 is negative root 2 over 2, right? And that's about negative 0.7. So can we plot negative 0.7 in the 3 pi over 4 direction? Yeah, we'll go this way, 0.7. Yes, in the opposite direction, that's about here. Yeah? 2 pi over 3. The cosine of 2 pi over 3 is back here. The cosine of 2 pi over 3 is what? Negative 1/2. So I'm going to go in the 2 pi over 3 direction, negative 1/2, so I'll be going back here, yes? Halfway in between? Huh? Oh, very nice. All the way to pi. So in the pi direction, I'm going to plot negative 1. Can I do that? Yeah, I have to go back this way. Oh, I see. Yeah? Cool. So 5 pi over 4, cosine of 5 pi over 4 is negative root 2 over 2, and that's about negative 0.7. So in the 5 pi over 4 direction, I want to go negative 0.7. Oh, there it is again. Yes? 3 pi over 2, and now we start seeing the pattern. So 3 pi over 2 would be in this direction. I want to plot 0 in that direction. Now we're back to positive function values correspond to positive r values, right? And so what's convenient after 3 pi over 2? How about 5 pi over 3? I'm going to go in the 5 pi over 3 direction. 1/2. Hey, I can do that. There's the 5 pi over 3 direction. I'm going to plot 1/2. A radius of 1/2. Yes? Awesome. And can we go all the way to 2 pi now? The cosine of 2 pi is positive 1, a radius of positive 1 in the 2 pi direction is back to here. Are you seeing that this also produces a circle? But this time my orientation is slightly different. Right? When my r was based on sine of theta, right, I had that orientation. Now I have this orientation. If I continue the graph, right, if I continue the graph of cosine in the Cartesian plane for the left or the right, I just continue tracing the circle around. You guys see that? It's pretty sweet. So more about those orientations next class when we look at our polar graphing activity and some function families. But first, let's go ahead and see if we can't deal with some more complicated pictures. Consider the function f of x given by 3 plus 2 cosine of x in the Cartesian plane, I went ahead and changed the scale here. Let's go ahead and see what makes sense. It looks like we've got quadrant 1 here. Oh, I see. Remember that +3 outside? That's going to change my center line, right, of my cosine function graph. The period looks like it remains unchanged, but that 2 multiplier, what does that 2 do? Yeah, that affects my amplitude, my wave height above and below my center line. So I'll go ahead and add some key things like my center line. It's going to be y equals 3. We can add that in. Amplitude, Sydney says is 2. And our window we can still do, looks like pi over 2, pi, 3 pi over 2, 2 pi. Yes? All right, let's go ahead and see if we can produce a graph. So from our center line 3, it looks like cosine starts at a max in relation to my center line. It's a positive 2 cosine, and so it looks like I'll go up to my maximum. Center line, min, center line, max, center line, min, center line forever in quarter period increments. You guys got it? Yes, pretty picture? Oh, you guys look good. So your graphs. Nice work. Oh, guys. I miss being away. All right, let's go ahead and take our function values, f of x. Remember, our function values now are going to correspond to our new radius values. And so let's go ahead and consider at an angle, direction of 0, right, radians. That's in this direction. My initial r value is what? Well, my initial r value is, we're at a magnitude of 5. You guys see that? Look at that. Our function value of 5 corresponds to our radius value in the polar coordinate plane. So let's go ahead and start ticking. 1, 2, 3, 4, all the way over here. You guys see that? 1, 2, 3, 4, 5. Let's start ticking. And what would be another convenient one? Let's do power 4. So pi over 4, well, let's do pi over 2 first and come back to pi over 4. Maybe that'll be easier. How's that? So pi over 2 direction. What's our function value? Our function value is on the center line, so that's 3, isn't it? So what's our r value? 3. Can I go 3 in the pi over 2 direction? Yes. So 1, 2, 3. So right here? Huh? Cool. So we'll go ahead and keep getting our key points and then come back and fill in some of those. In the pi direction, we want to travel an r value of what? 1. You guys see that? That corresponds to that point in the coordinate plane. In the 3 pi over 2 direction, we want to travel an r value of what? 3. So we're going to go 3 in the 3 pi over 2 direction. That is right here. That's pretty sweet. And a big key point before you're still filling in the blanks. In a direction of 2 pi, we're going to travel, back to 5 again. You guys see that? It looks like, does it look like a circle?
No.
This does not look like a circle again, okay? Let's go ahead and fill in some intermediate points now. Let's consider pi over 4, back to pi over 4. So pi over 4, the cosine of pi over 4 is about 0.7, right? 2 times 0.7 is about 1.4. 1.4 plus 3 is about 4.4. Let's try. Let's try going about 4.4. Do we want that? 0.7 times 2, 1.4. 4.1, yeah? Can you do that? We're gonna try it. So let's go about 4.4. 1, 2, 3, 4.4. How's that? Yeah? What else would be easy? Pi over 3? Pi over 3 would be easy? Pi over 3, cosine of pi over 3 is 1/2.
Yeah.
Times 2 is
1.
1. Plus 3 is
4.
4. Let's go in the pi over 3 direction 4. Hey, this is coming together. Okay? What else would be easy? 2 pi over 3 would be easy for cosine. 2 pi over 3 would be easy. Let's do 2 pi over 3. So the cosine of 2 pi over 3 is negative 1/2 times 2 is negative 1 plus 3 is positive 2. Let's go in the 2 pi over 3 direction, positive 2. Ah. Another easy value, right? Another easy value for cosine would be 4 pi over 3. Can we do 4 pi over 3? So cosine of 4 pi over 3 is negative 1/2 times 2 is negative 1 plus 3 is positive 2. Let's go positive 2. There we go. We can do one tricky value. Let's do one tricky value. Let's do 5 pi over 4. Cosine of 5 pi over 4 is negative root 2 over 2. That's negative 0.7. Negative 0.7 times 2 is about negative 1.4. Negative 1.4 plus 3 is about 1.6. You guys get it? 1.6? Let's try it. Huh. I want to do one more to confirm what we're seeing here. I'm going to go back to 3 pi over 4. So 3 pi over 4, cosine of 3 pi over 4 is root 2 over 2, negative root 2 over 2, which is about negative 0.7, times 2 is about negative 1.4 plus 3 is about 1.6. 1.6. Oh my goodness gracious. Easy value, 5 pi over 3. Let's get back to our easy values. 5 pi over 3. Cosine of 5 pi over 3 is positive 1/2. 2 times 1/2 is 1 plus 3 is 4. Let's plot 4 in the 5 pi over 3 direction. Ha ha. That's very easy. That was great. Let's do more of those. And finally 7 pi over 4. 7 pi over 4. So 7 pi over 4. Cosine of 7. Is that us?
Whoa.
Is this number 3 or number 4? Number 3. Darn it! I want to finish it up by doing this. I was excited. I am excited. Let's finish this up and then I'll stop the recording. Oh, look at this. Look at that dimple. Oh. What does that look like? It's kind of like a heart because it's called a cardioid. It's actually called a cardioid, and more on that next time.
Time just flew by today.